Good morning and welcome to the last day of ICLA. It is my great pleasure to introduce our invited speaker, Gabriel Sandu. Gabriel has been one of the founders of independence-friendly logic, which changed the face of the way, changed the way people looked at first-order logic, I believe. And he has we will talk about probabilistic independence-friendly logic.
Well, thank you for these very kind words. Good morning. I'm very grateful to both Ramanujan and Kamal for having the opportunity to present this topic here. I apologize to those who have heard these parts of this talk before. I'm going to present some of the main concepts that have arisen in this independence-friendly logic. It is a system of logic which is developed by a relatively, well, I'd say small community. It was initiated by my teacher. I introduced you actually as my teacher, Jaakko Hintikka, but I mean, he has done the previous work on similar things, like the branching quantifiers. And so a very short motivation, as historical motivation, it should be enough to say that among the three conceptions of quantifiers that we have in the recent development in the modern development of logic, I mean quantifiers as algebraic manipulations of sum of products. This is a Schroeder school. Then we had the sort of Frege and Montague school of quantifier, which sort of added content into logic. And then finally we had a Skolem-Hilbert conception of quantifiers, which looked at quantifiers as especially quantifier dependence and the relation with choice functions. It is this last conception which was precisely at the heart of how mathematical logicians thought about logic and about the quantifiers in the 20th century. So it is the independence-friendly logic, it inscribes itself in this particular conception. Then as a systematic conception, I just borrow a few examples, a few considerations from one of the field's medalist, Terence Tao. I do not want to say that he would endorse anything of what I have to say here, but that's neither was he instrumentalist in helping us to frame this conception, but I thought that this might serve as a natural way of introducing that. So we know how in first-order logic we can express statements like these ones. For every x there is a y, which depends only on x, such that a relation B holds between x and y, and express it in that way. We also know that how to express for every x there is a y which is independent of x, such that the same relation holds, and that we do that by showing there is a y for all x, and then B is a y. When we have four quantifiers, things become a little bit more complicated, but still we can express naturally things like for every x prime, and x second there is the y dependent only on x and x prime, such that the appropriate relation holds. We do it in that way, and so having, as we say, there is a y in the scope of both universal quantifiers. It depends of, but so concrete examples from mathematics are easy to come by. For instance, the continuity of a function f at a point x0 is defined by the Cauchy-Weierstrass delta epsilon technique. So for every given a point x0, if a function is continuous at x0 if given any epsilon strictly greater than 0, one can choose delta strictly greater than 0, so that for all y, then we have the distance between x0 and y. If the distance is smaller than delta, then the distance of the images is smaller than epsilon. So the general form in this case is the one that is mentioned there. So the choice of y depends on both x0 and epsilon. Sometimes it turns out that, the choice of delta depends only on epsilon and not on the point x0. So in this case, we'll have a statement of the general form that for every x prime and x second, there exists a y depending only on x prime, such the relation holds. And then we can rearrange the quantifiers in such a way that, that we obtain the desired dependencies, as in the formula above. So we notice the difference between continuity and then uniform continuity, which is reflected still we have a linear order of the quantifier, but it's reflected in the relevant scopes of them. Now, we cannot always express a statement like for every x and x prime there exists a y depending only on x and the y prime depending only on x prime, such that the relation holds. So we cannot always express that. And I mean, then Tao expressed that by saying that it seems to me that first order logic is limited by the linear and thus totally ordered nature of its sentences. Every new variable which is introduced must be allowed to depend on all the previous variables introduced to the left of that variable. So this does not fully capture all of the dependency trees of variables which one deals in mathematics. So he adds that even if we add first order logic with set theory, that will not improve the situation. And I'm not going to enter into that.
Who is Terence Tao?
Sorry?
Who is Terence Tao?
He is one of the Fields medalists in mathematics.
This is a recent statement?
That is from 2007.
So shouldn't the credit go to Henke?
Yes. Well, he actually, yes, the glory should go to Henkin. Actually, Terence Tao doesn't mention Henkin or anybody else, but he says that he is aware that logicians have been, I mean, he knows that logicians have been aware of this phenomena for a longer time. Yes. So well, he actually says that, also writes that, well, we should, second order logic might be a medicine for such a thing, but he thinks that second order logic is an overkill. It's nothing wrong, he says, also at the end of working with plain natural language. But, well, yes, that's... So, looking at Henkin sentences, there are different formulas to deal with this problem mentioned also by Terence Tao. And one of them was, as Rohit mentioned, was the Henkin quantifier approach. But then there are various reasons why, when I started to work on this in Synthetica, then we prefer these formulas. I might say something why at the end of my talk. So we consider extension of first order logic with quantifiers and connectives of this form, and where W is just a set of variables. The intended interpretation is that the quantifier, the choice of X, for instance, is independent of the values of the variables in W. So when W is equals, it's empty, then we recover the standard quantifiers. So a sentence like the one containing the 4 quantifiers that cannot be expressed in first order logic will have this form. For all x prime, there is a y, which is independent of x prime, and a y prime, which is independent of x and y, such that the relation holds. Now, an example would be this sentence which has 4 quantifiers, which turns out to be equivalent, or it turns out according to one of the interpretations that I'm going to quickly sketch below, is going to be interpreted with the reason f, so that for all x, f of x equals x, and x is distinct from x. So it is now that sentences like this are not first order definable. So the 3 kinds of semantical interpretation have been offered for this kind of languages, and one of them is the original one that I had in mind with Syntica is a game theoretical interpretation, semantical games of imperfect information. And then the second one, which is actually quite straightforward from it, it's semantic in terms of Scholen functions and Kreisel counterexamples. And then the one which motivated most of the work done by mathematicians like, well, I'll say something about that, is a generalization of Tarski semantics, which is given by Wilfried Hodges in a paper in 1997, which has stimulated further work in this area. So this is very briefly, so we consider such an IF formula and then an assignment which includes its 3 variables and an appropriate structure M, and then we play a game, a semantical game, which is an extensive game by 2 players, the existential universal player. We call them sometimes following Hodges, Eloise and Abelard. And then so it's just Eloise tries to verify the sentence and tries to show that phi is true, and Abelard tries to show that it is false. And then at the beginning of the game, Eloise is a verifying player and Abelard the falsifying one. So the players move sequentially in the game, and until they reach an atomic formula when the game stops. And then when the atomic formula and the corresponding assignment, which extends the initial assignment, verify the formula in the model, then the player who is the falsifier at the time wins. There was a mistake here. Yes, well, no. And otherwise, the falsifier wins. So there is a mistake there. When the negation phi, I should have written the players play phi and the assignment there with role inverse. So negation is treated game theoretically by the inversion of the roles. And then for disjunction and existential quantifier, it is the verifier, the player who is the verifier who makes the moves. And for conjunction and the universal quantifier is the player who is the falsifier. And when a play of the game ends up, then we have just 2 situations. As I said, either the atomic formula is satisfied by the corresponding assignment, in which case the Eloise, I mean the existential, the verifier, the player who is the verifier wins, otherwise the falsifier wins. So what is important in these games of imperfect information is that the way you teach strategy, so well, this is a standard way to do it in this case. So we have, strategy must be uniform. So a strategy is, like usually any method, which will give the player a way to make his choices. And but the important thing is that, well, you can think of a semantical game as a tree. The important thing is that there are certain histories which are equivalent. We call them W equivalent in this case. So I prefer, instead of giving the formal definition, just to illustrate as an example, if we have, for instance, a formula like the one I have here, and then just imagine that we have different branches of the trees, and then we have reached this formula. So it is actually it is the existential player which must make a choice. The verifying player must make a choice corresponding to the existential quantifier. There is a y, and then well, you think of any 2 histories which have been of the trees corresponding to the elements, to the individuals A1, A8, or B1, B8, which have been chosen as values for X1, X8. Then they are X1 and X5 equivalent if then they coincide all the elements except 1 and 5. So they must coincide with all the elements outside the set W. And so when any such histories are W equivalent, then the strategy must be constant on them. So the truth and falsity is just simply the existence of a winning strategy for either one of the players. So truth, in game theoretical semantics, the existence of a winning strategy for existential player, and falsity, the existence of a winning strategy for the universal quantifier. And when we deal with the classical first order sentence phi, first order formula phi, then we apply the Ermelo theorem, and we know that the game is determinate. But the slash quantifiers, they introduce two phenomena into the game. So one phenomenon is indeterminacy, and the other one is signaling. So indeterminate synthesis, they have been much discussed in the IF literature, and the first one, the indexes MPs come from matching pennies. So this is the game expressing somehow the matching pennies, because he just said that for all x there is a y independent of x, so the existential player, when he makes a choice, he doesn't see the value of x, but he has to choose an identical element. And so it's easy to see that this is logically indeterminate. Well, we exclude models with one elements here. It doesn't make sense to, in the context of independent quantifiers, to talk about models of one element. So it's all the models contains at least two elements. So this the matching penny sentence needs a true nor false, and the same for the inverted matching penny. So the existential player then wins if he is able to mismatch the choice of his opponent, and so none of them is true nor false in any model. And the same is the sentence expressing infinity, which is the last sentence here. It's defined infinity and it is, so it just says that there is an injection whose image is not the whole, whose range sort is, whose image is not the whole universe. So this sentence is indeterminate also on all finite models. The signaling coordination is something which has been noticed by Wilfrid Hodges, and he just noted that if we take the first sentence, the matching penny sentence, which, as I said, is logically indeterminate, then just by inserting a dummy quantifier in between x and y, so insert a z universal for all that, which doesn't play any role further on. But one is able to change the truth value of a sentence, so to change an indeterminate sentence to a logical truth. This is just, so in this case, if we think of the existential player as consisting of two members, there is a z corresponding to the two existential quantifiers, then we can think that the two existential players, they can coordinate each other. And so finally, and the coordination is quite simple, isn't it? The z just matches, z sees the universal quantifier, he just matches, copies the value of x, and then y, the second existential player, even if he doesn't see the value of x, then he sees the value of his partner, and he copies, or she copies that, and she will manage to verify, the existential team will manage to verify the identity. So in this context, perhaps it's good to mention some other frameworks which have been developed for that, which have been perhaps presented also to this audience, and that is dependence logic of Venenen. Venenen published a book, Dependence Logic, in 2007, but that inspired some, by Hodges and Venenen, Abramsky and Venenen and others. Abramsky, I think in 2010, he published a paper which is called independence logic versus dependence logic, a tale of love and separation, and that is so if you look at for all x there is z, there is a y, independent of x, that sentence. It's I mean, these people, they want to they want to render it in their formalism by saying, well, why don't you take just the linear quantifiers, and then so unslash quantifier, and then express all the relevant dependencies just by these atoms. So the identity, it's a confusion here of the notation, but it just said that x equals y and z is independent. Z is dependent on x and y is dependent on that. So it depends on which kind of method you like to sort of favor. It's whether you like to favor compositional methods, and in order to favor compositional methods, it's better that you have all the dependence representation in the atoms, so that you can start the semantical clauses by induction. But this is not how I thought of it with Syntica. We prefer the game theoretical interpretation as a signaling phenomena, because I think that will allow us to sort of account for different strategical and game theoretical phenomena more than the independence one. So I think that very much the distinction between the two frameworks can be spelled out in terms of, well, do we want to have a compositional generalization, Tarski type interpretation, or do we like to still play on the game? So we do prefer the signaling, the logic, IF logic, with this sort of signaling phenomena. And so let me give just a couple of examples taken from Janssen and Duchesne, to a couple of examples of signaling. So if you have this sentence, you can think, as I alluded to, of the existential team. Existential players, as consists of two players. One is a disjunction, and the other one is the existential quantifier. And then that is also a logical truth. Well, the winning strategy for the existential player is just let the universal player choose two values for x and z, and then, of course, if the chosen element they are equal, the chosen element if they are distinct, then the disjunction chooses left, and then if they are unequal, they chooses right, and then after that it chooses z. Even if the existential player doesn't see the value of x, she sees it's the other value, the value of she chooses z, which she sees. And another example is again, yes.
So you say that basically everybody decides what to choose depending on whether x is different from z or not.
Yes.
How does that happen in practice if the analyst cannot see the value of x? So how can she? Is it the molecule that tells the truth of this atomic formula? Or?
But at the level of when she chooses, she sees so she has to take she chooses a disjunct. But at the stage where she chooses a disjunct, she sees those values. And then at the next level, when there is a move for the existential player, then she doesn't eat it, but she has seen her previous moves, and because she has seen her previous choice, then there is this kind of coordination between them. So she has seen that. So that is a strategy. If x equals z, then the existential player chooses right, after which Eloise chooses z that she sees. So she sees a z.
Yeah.
Okay. Yes?
So it looks like we have a theorem which says that the sentence is a logical truth, even though if there is a strategy for the compression.
Could you say?
I'm just wondering, it looks from your slides as if you have a theorem saying that the sentence is a logical truth, if and only if there is a strategy for the extension layer.
It is, well, it is, there is a winning strategy for existential player in every model. So, but I do not, I ignore the model here. I know the model here because every model contains at least 2 elements. So it will be seen to work in all similar cases. Yes, yes, yes. Okay. So that is, well, a little bit more involved example from the same paper. And this, again, this is a logical contradiction, so which is false. In every model is at least 2 elements. And so again, I ignore the model here. And this, again, we think of the universal player as having 3 players corresponding conjunction. The first universal quantifier and the second one, and then the strategy is sketched here. So you have a similar phenomena that at the level when the Abelard has to choose for disjunction, he sees all the moves by his opponent, but then his partners later on, they exploit this fact. And so this is phenomena of signaling. I'll not run through it, but so I'm not going to run over that topic, decomposing always a strategy into Scholen functions. That's straightforward, and it just, you see, you just have to take care that the arguments of the Scholen functions are actually the values that Eloisa sees, and the arguments of the, well, I'm giving an example here. I'm running out of time, and the decomposing Abelard structure into Kreisler example is also straightforward. So an intriguing phenomena which has provoked some discussion in the IF literature is behavior in the existential quantifier. So we have this sentence: there is an x, there is a y, which is dependent over x equals y. That's a logical truth. So that is equivalent with the sentence: there is an x, there is a y, x equals y. So the question is, can we always remove independence from existential quantifiers? And of course not. And actually we have a counterexample here. For all x there is a y, there is a z which is independent of x and y, so that x equals z. That is logically indeterminate, so in every model with at least 2 elements, there is no winning strategy for either players. So that we cannot always remove existentials, independence from existential quantifiers. So what about, so are declarations, expressed that in this sort of metaphorical way, are declaration of independence from existential quantifier irrelevant only in existential formulas? So, because here we had a sort of counterexample which involved a universal quantifier. And that has been a problem which, at least for me and some of my colleagues, is not easy to solve. Because, well, it is not that we have also sentences which involve universal quantifiers, or where you can safely remove the independence of existential quantifiers, like these ones. So these sentences are equivalent. They are both logically determinate, even if in the second one we removed the independence of that from y. So that, there are a little bit of, we have studied this phenomena. So what is a relevant dependency independence, which and the only way we sort of we managed to find is rather to study prefixes of existential quantifiers and universal quantifiers. We know anyhow that the IF logic has a prenex normal form. How we do, and we come up with, so first of all, we had to define what is sort of relevance of independence. So if we are concerned once more, I concerned with this phenomenon. We have there is a x, which or a slash big X, and then which later on there is a y slash y, which is in the scope of the formula, so that x belongs to y. This means that that there is a y, that quantifier is independent of x. So then one concept of relevance that we came with is it's actually very weak. It's just to say that the independence of y from x is relevant if there is a sentence. It's a formula in this psi, but we can form a sentence by prefixing the quantifier to that sentence and the structure to that formula, and the structure M such that that formula and then the other formula in which we erase x from y, so in which the existential quantifier y is not any longer independent of x, they have a different truth values. So there is a situation in which the two formulas can be distinguished. They have different truth and falsity values on them. So this second formula, q, the sequence of quantifiers q, and then the index there just means that we have y is not any longer independent of x. So when we erase the independence, then they have truth value. So it makes a difference. That is so it's relevant. And the so it's and then we come up with notions which are probably known in the computer science literature, like breaking knowledge memory. Well, this is not actually the lack of the imperfect recall that they study. We just deal with these prefixes and with the independent of an existential quantifier from another existential quantifier, and so so again, let the existential quantifier be in the scope of the there is a y, in the scope of there is an x, and so that y is independent of x, and the independence of y from x breaks knowledge memory, of course, if there is a universal quantifier that we set at some stage, the first stage there is an x knew what the value of the universal quantifier is, but he doesn't know it at a later stage. So there are things like, well, it's this is a student of mine who we work this. I mean, he's publishing a paper on this, and well, there's probably if the independence of y from x breaks knowledge memory in a quantifier for x, then it is relevant. So results like this. Or then we have another concept, broken signaling sequence. So we have a sequence of quantifiers like here that is actually inspired by the Hodges sentence. So we have what the four conditions here say that, well, you see, it's we start from, so there is, we start from, there is a v k minus 1. He sees v for all v. Then always the following quantifier sees the preceding one. And then it's called, so there is this phenomenon of signaling. So we always start from, we can start from, there is an x sees there is v1, which sees there is v2, etc., until there is a v chi minus 1 sees the universal quantifier. But then the signal sequence become broken when the last one, there is y. I mean, he doesn't see any of the other sequence. So that's why x belongs to y, but also all the other variables, v1 up to vk, belongs to y. So it broke the signaling sequence. And the kind of, well, there are some examples here. For instance, we have this signaling sequence. v1 sees v2, then there is an x sees v1, but then there is a y, doesn't see any of them. And the kind of characterization results that was given was that the independence of y from x is relevant. So it makes a difference in our sense of relevance, if and only if the sequence of it can be embedded in a sequence, in a broken sequence, broken signaling sequence. I could say more about this, but perhaps I should move forward. So, a suggestion which was made by Aitai, which is quoted in Blaž and Gurevich 86, was that there is a way to overcome the indeterminacy of IF sentences. And that is simply to use von Neumann's minimal theorem to such sentences, indeterminate sentences like the matching penny sentence, the inverted matching penny sentence, play on finite modulus n elements. So the value of, for instance, we let the value now for x there is a y, independent of x equals y, to be 1 divided by n. And that is given by the minimal theorem in this sentence, for Neumann minimal theorems. And similarly, for the inverted matching pennies, is given by n minus 1 divided by n. So we suggested the technique is actually due to, it is Melvin Sylvester, I mean, in ILSC, who developed, developed this technique in his doctoral dissertation in 2006, and then I wrote a paper with them, and then we developed that version in the book which appeared 2 years ago. So that's a very insightful thing to do. I mean, in my opinion, so you know how one can move from this sort of model theoretical thinking or reasoning to the probabilistic thinking. But if you think of the two sentences that I put there on the table, the matching penny and the inverted matching penny, they cannot be distinguished by the game theoretical interpretation. And so, but then at this point, it makes sense. But still, intuitively, there is a difference between them. I mean, the odds of existential player winning the first game is 1n, and it decreases all the time as the underlying model increases. The odds of the existential player of winning the second plane is n minus 1 by n, so it increases all the time as the model increases. There is no way to separate the two sentences if we stick to the game theoretical semantics, but there is a way if we switch to the probabilistic interpretation. So we move to the strategic game. Well, strategic game, well, this definition is well known. We are just in the case of a two-player strategic game, and I'm not going to, but we are interested in strategic games which are defined by IF sentences. And then, so the strategies of the existential player are going to be, in this strategy game, are going to be her strategies from the semantical extensive games. The strategies of the universal player are going to be, I mean, his strategies from the extensive semantical game. And then the utility functions are defined straightforward. Well, I mean, the existential player, she plays a strategy sigma against the universal player who plays a strategy pi, and then when they play that, a history, a play of the extensive game is obtained, and then if the payoffs for those particular strategies are obtained directly from there. And so we have an example. We have this matching pennies and extensive inverted matching pennies. They are played on a model with 4 elements. So on the left side, we have the matching pennies example, and you see that the existential player, I mean, he wins just on the diagonal because it's only then when the 2 elements are equal. And so 1, 2, 3, 4. Once again, I'm probably going too quickly, or too slowly, perhaps, are the strategies of the existential player. Then 1, 2, 3, 4 are the strategies of universal players, and then the 2 strategic games are here. There are no equilibria in either game, and so it's natural to do what the game theorists have done for a long time. We move to mixed strategies, well, a mixed strategy is just a probability distribution over the set of pure strategies for the players. And then the notion of expected utility in the game for either player is formulated the standard way. And then we can apply this mixed strategy equilibrium notion, and which is again is standard, and then the von Neumann minima theorem. So I have done nothing else but sort of spelled out explicitly the suggestion by Miklos Aitai, and so the notion of equilibria defines a relation V between strategic IF games and values V in the interval 0, 1. And we know that this V is functional because every finite constant sum two-player game has an equilibrium mixed strategy. That's a von Neumann minima theorem. And then its corollary said that every two such equilibria gives you the same expected utility. So the equilibrium, Nash equilibrium semantics, we call it that, but the equilibrium semantics is a conservative extension of the interpretation of the classical game theoretical interpretation. So if a sentence is game theoretically true, its value is going to be 1. And if it is game theoretically false, so it is the sentence, then you have the usual values, truth and falsity.
Psi is a typo, right? The last line.
Yes, it is a typo. Thank you. So if we return to the two sentences, which I have spoken, which I presented before, then the uniform probability distributions here, they just form an equilibrium in both games. So the value of the first game is 1 divided by 4, and the value of the second game is 0.75. So as the size of M increases, the value of the sentence, the first sentence, is asymptotically approaches 0, and that of the inverted magic penny asymptotically approaches 1. So this is the same kind of method will show you that in the case of the sentence defining infinity, which I listed before, mentioned before, then this value on finite models is going to be n minus 1 divided by n. So as the size of the universe increases, so its value is going to approach truth. It's going to approach 1. So one can show that expressions of rationals for a rational number q, there exists a sentence that has value q on every structure with at least 2 objects. So the values of the IF sentences under this equilibrium semantics covers just a set of rationals. That is well, that's a little bit. So here you can determine the value of an IF sentence by bringing into play some more of the machineries of game theory, like iterated elimination of dominated strategies. So the informal description of the game is well, it's that's I'm going actually to skip over this, but the IF sentence defining that is just going to be express F. So the universal player is going to pick M elements from the universe, and then the existential player is going to pick one element from those without seeing the choices made by the universal player. And then the true sentence is beta 1, beta 2, beta 3. They just spell out the winning condition for the existential player. So well, the game theoretical probabilities, we can extend that. We can internalize part of this semantics into the object language, so introduce a new term. Nash equilibrium phi equals L just means that the value that is true in a given model, if and only if the value of phi in M is R, the value of phi under this equilibrium semantics is R. So we have this conservativity that I mentioned before, so we showed earlier with Manet and Sylvester that the Nash equilibrium, I mean the equilibrium semantics, obey these examples, these principles. So it's a minimum for conjunction, the maximum for conjunction. And then for the negation, the game theoretical negation, it's 1 minus phi. Remember, we are in the case of IF logic, so they are indeterminate sentences in the logic. So it follows that the following also principles are obtained, which I mentioned them as axioms. And the Nash equilibrium of any sentence is greater than 0, and then we have them here. So the probability interpretation obeys the Kolmogorov axioms of probability. So it's nice to put this into a perhaps larger setting. We have these two conceptions of probabilities, roughly, which have the probabilities as proportions of relative frequencies. And then we have probabilities, subjective probabilities as degrees of belief. Usually the difference between them is illustrated by these two statements. The first statement is, for instance, the probability that a randomly chosen bird flies is greater than 0.9. And the second one is the probability that Tweety, a particular bird, flies is greater than 0.9. So the first one is said to be a statement, claims something about the world, one world. There's a sort of relative frequency. And the second one is, despite perhaps its appearance, is something about the agent's belief. So my belief that has degree 0.9. And that is something that I learned from papers by among other, a paper by Halpern and Bacchus. So there are two different formal approaches that they've been developed to deal with this kind of interpretation of probabilities. One of them is that is you take a probability distribution of the universe, of the individual in the universe. So you add to the syntax of first order logic a new term, W with subindex x, and applies to phi. Phi is a sentence of first order logic. So the intended interpretation of that term is that the probability that a randomly chosen x has a property phi. These are sentences which are interpreted on probability models. They are like first order models, except that you add the probability distribution of the individuals, and then you can define in a natural way the probability of a subset of the universe and so on. And now the clause which interests us here is that, well, when the subscript contains is a vector of distinct variables, in the last clause, then its value in a model and with respect to an assignment is just a probability that a sequence satisfies the formula phi. So the second interpretation, which is the degree of belief interpretation, it just takes probability distributions of possible worlds. Again, we have a new term, but this new term is not any longer binding a variable. It's just applied to a formula, to a sentence of propositional logic or first order logic, and then you interpret it in probability models, and the probability model now is the probability distribution is now over possible worlds. So the clause which again matches the clause of the probability distribution of the statistical probability approach is the last one, which says, well, the value of the sentence phi in a given model is just you calculate the computer probability of the possible worlds which satisfy that. So the game theory of the probabilities that must have been pointed out in the literature somehow is that, so we have a sort of, I would say not a sort of, but we have a third interpretation of probabilities. So we have, I just very quickly mentioned through three logical formalisms, which corresponds to a three conception of probability that we have. One corresponds or captures probability distribution over the individuals in a given universe, one universe, which is our world. The other one, which was the second one, which captures probability distribution over possible worlds, which corresponds to degrees of belief. And now we have this Nash equilibrium phi. Phi is now a sentence of IF logic, which corresponds to probability distribution over strategies of the players from the Nash equilibrium, which arises from them. And it's interesting that syntactically, it behaves like the second one. Semantic, in a sense, we have the probability distributions over strategies in our world. But, well, there are things to say, but perhaps the fact that it resembles syntactically that, it has probably something to do with the fact that, well, perhaps a reasonable way to understand the Nash equilibrium is just in terms of beliefs. And so this is one further point, aspect of future research. So, and just very simply, these are some things which I am dealing in a present paper, which is going to appear in a handbook edited by Sujata Ghosh and Rineke Verbrugge and Johan van Bentem on strategic reasoning. I just try to apply this to epistemic, all sorts of epistemic puzzles. This is one of them, the Monty Hall puzzle. You have 3 doors. Behind one of them there is a prize, the other 2 are empty. The contestant C chooses a door. Monty Hall opens any of the other doors, which is empty. Then she asks C whether she would like to switch the door and choose the remaining one, which is closed. Is it in C's interest to do it? So you express this in IF logic in the first formula there for all x. You have to think of that. For all doors, there is a choice, there is a guess, the existential quantifier does without seeing x. So that for all doors that Monty Hall opens later, if that door is independent of the door with the prize, and the door chosen by the existential player, by the contestant, is also distinct from the door opened by Monty Hall, then the existential player has one final choice to make. And she has to identify, her choice T has to identify X, the door with the prize. Can she do it? So we can explicitly express things like the state strategy or the street strategy, and so on. That's for the investigation. Another problem that can be expressed are with signaling systems, coordination problems, but I do not have time to run into that. So that I'm just to close just by telling you that this is the game theory frameworks, which work for first order sentences, quite naturally lends itself to if you consider first order logic, which are games of imperfect information, or perfect information, then you go to first order logic, games of imperfect information, quite naturally via these slash quantifiers, and then you exploit results from game theory to get a probabilistic interpretation for IF sentences when the corresponding the underlying sentences are undecidable. And then the aim of future research is to study some of these puzzles and perhaps to see how probably their solution depends on some of the syntactical properties of the formulas. I hope I was not too fast. I thank you very much for the patience. That's all I had to say.
I very much like what you are doing, because I think the direction of bringing in standard game theory into IF logic, I think it's a brilliant idea, and I think it's a natural one. I have a general question about IF logic. As you know, there was a result that Vananan and I proved that if you, in IF logic, if you restrict each existential quantifier to have only finite amount of information about the preceding moves, then the logic becomes decidable. Now you also have the case of the first order logic, where if the dependence functions are linearly ordered in terms of the dependence, then of course you have recursive axiomatizability, right? Now, in the case of IF logic in general, we know it's highly undecidable, but these two cases show that there are decidable or at least RE subcases. What do we know about the general case of you put these restrictions on the strategies and then the logic becomes more amenable? How much is known about that?
I know. I don't know any results. I think that one of Yoko's people, perhaps Nurmi or somebody, he has dealt with the subfragments of IF logic, which is decidable.
Yeah.
But I don't know exactly which. And then there is a forthcoming paper by Continent and Givenena, which addresses the question of the completeness of the set of logical truths which are first order consequences only of ranking quantifiers. But I do not know anything about decidability results of the sort that you mentioned. So I would venture to say that is pretty much an open question. Yes.
Okay.
Yeah, more sort of philosophical question or conceptual question. So in dependence and independence-friendly logic, the concept of choice is used to explain a quantification issue. On the one hand, on the other hand, we have this Hilbert choice operator, right? And once you have that in predicate logic, then you can define quantification. So I was just wondering whether maybe a predicate logic with Hilbert's choice operator would be something more primitive, more foundational than, so if one could maybe use that kind of logic to explain or to give semantics or an interpretation to your independence-friendly logic, or maybe even also dependence logic. Does that make any sense to ask this question?
So is it so that the epsilon operator, I mean in Hilbert, does it take you outside the first order?
Sorry?
Does it take you the epsilon operator? I mean,
yes.
Does it take you outside first order logic?
No, I don't think so.
Well, I don't think so. I mean, there is Caicedo has written something about that. Xavier Caicedo has written something about the first order logic and I mean, from a technical point of view. But I mean, my doubts, I sort of investigated that would be a natural thing, but I investigated the possibility with sync at some point, and then we didn't see, I mean, any possibility to reach, I mean, for arbitrary part of the independence, which goes beyond also first order logic with the choice operator that you mentioned. But but I wouldn't be definitive about that. So, but that's of course a natural suggestion to come with one man.
Thank you.
Thank you. Yes.
Thank you.
Yeah, Gabriel, we know it's easy to represent partially ordered quantifiers in second order logic, and Hintiker has responded, if I remember correctly, by saying that the advantage of the game theory comes when you start putting restrictions on the kind of strategies that are allowed. Is there anything in the phenomena you've talked about this morning, is any work being done to say what happens if you tried to represent them in second order logic in a way which might help decide this issue as to which of these ways is preferable? I mean, if you tried to say, look, this is going to be a part of second order logic, how do we represent the various things you've told us? And that might help to decide the issue as to whether you should prefer to take second order logic. I'm thinking now more in for the semantics of natural language, where clearly it's got to be second order, whether the second order is quantifying over strategies or whether it's quantifying in another sort of way.
Well, that is a different question. I mean, of course, there is a way. So there is a way to put restriction of the quantifiers, which Hintiker himself does in, for instance, just restrict the quantifiers to the existential functions, to computable ones. So, and then, well, he claims that he obtains a particular interpretation of intuitionistic logic, and but then you would say that you'll find it more naturally that to work with the second order fragment. You think that is more appropriate for representing things in natural language than the IF approach. Did I understand you correctly?
Well, I mean, I agree with Hintiker that there's a lot of, if you like, second order. I tend to think of things like each as critics. Some critics admire only one another, or every philosopher in India could fit into this room, and so on, where for me, naturally, I tend to think in terms of quantification, second order quantification. But I do know that, I mean, Hintiker is well aware of that issue, and has, as I recall, it was his remark that when you start putting restrictions on the kind of strategies that are allowed, then you can see all sorts of advantages in the game theory way. And I wondered whether the things that you were talking about this morning looked like putting restrictions on the kind of strategies or describing the kind of strategies that are allowed. And I wondered whether you might want to say it becomes less natural if you tried to do this in an ordinary second order logic.
Well, these are very good suggestions. Self, in his research, he works much more with, I mean, there is a natural way, of course, he deals more with the question of dependence and how to resolve paradoxes and the notion of predicativity and predicativity and what is relation to dependence. So we are looking very much for other notion of dependence and independence, which would be, useful for foundational mathematics, for paradox and all that, but we haven't explored the line that you mentioned beyond what was known until now, but thank you for that, yes.
This is a kind of a follow-up to Max's point and question. Now, in game theory, memory plays an important role in various kinds of strategies. One can consider a strategy with perfect recall, bounded memory, and so on. Whereas in the semantics of IF logics that you provide here, memory doesn't seem to feature, at least certainly not explicitly. But one could think, well, let's say, sort of purely by analogy, considering game semantics where strategies use memory to some extent. So my question is, could that provide any sort of meaningful logical semantics? That is, assuming some restrictions on the memory use. Can that make good sense from a logical viewpoint?
Well, I see. That's a very interesting question. So let me see if I interpret you right. So the problem with there's not a problem, but these are semantical things. So they just mean that there is a winning strategy for, even for first order logic, there is a winning strategy for one player per die, but this winning strategy is not uniform in the sense it just said that for every model there is a winning strategy, but then you like to get things like there is a winning strategy which works for all models in order to get some notion of uniformity of strategies and to say things which would more resemble like provability in first order logic. And then, but in order to do that, you'd say it will be perhaps interesting to restrict the memory of the players, and that might lead you so. So is that what you, could one rephrase what you say in this way?
Yes, the notion of winning strategy can be qualified.
Yes, but I'm afraid that will not be enough in that case. One has to also to extend, in order to apply the game semantics thing, one has also to extend not only the definition of the games, because all our games are trees, and probably one would have to consider games with all kind, with more moves, for instance, backward moves or to have, like in or parallel moves, like in one of the game semantics that I know. Yes, I don't know of any word like, Japaritse has done work on this. He just claimed that what he does is game theoretical semantics uses a few operators which put some restriction on the function that allow him to extract proofs from this kind of games. What you suggest, it goes in the same direction, I think. Yes.
Thank you.
So, thank you very much.